Welcome to Quantum Curious, and in today's video, I'm going to discuss a very important state of light that describes the classical light, and it is very uh, good approximation of a classical light in terms of quantum formalism. And this is very important from the experimental point of view because in most of the experiments, we are using the light that has uh, well-defined amplitude and a well-defined phase value. So far we have seen the quantum states that are not that much a good approximation in terms of a classical light because as we have seen in the case of the number states that have very random fluctuations of the phase, although they have very defined phase. So we will discuss that how the coherent states are very near or very good approximation of classical light and how can we define that kind of product states in the quantum formalism that we have so far reviewed. So let's start with the motivation that we have seen the fog states and we saw that they are very they are the states that have well-defined amplitude, but they have random phase value. So these are highly non-classical states. But uh, are there any kind of states that have well-defined values of amplitude and a fixed phase value, as in the case of classical field? So in the large limit of amplitude, we see that the coherent states behave the way that the classical fields behave. So we can say that the coherent states are the most classical states that we have in the quantum formalism. So let's review what are the coherent states. So coherent states are generally defined as the eigenstates of the annihilation operator. So we know that annihilation operator is a non-emission operator. So the coherent states cannot describe the eigenstates of any observable. So in order to write them in terms of some kind of observable, we can use number states because we know that they form the complete basis and they are orthogonal to each other. So writing the coherent states in terms of number states, uh, we can use the relation, this kind of relation that is the completeness relation. And we know that the overlap between the coherent state and the number state would be denoted as a number. And this is the correlation factor between coherent states and the number state. So we can see that we can define uh, the probability of photons in coherent states as the amplitude as the mod square of this value Cn. So our next goal is to find the Cn in order to write the coherent state as a superposition of number states. So we make use of this relation that we have described above as the coherent states are the eigenstates of the annihilation operator. So making use of this, we could write the coherent states as this as annihilation operator would uh, apply on the number state and would give that kind of relation. So in order to change the index in the get back to the n, we can make a change of variable by changing n is equal to n plus 1. We can write that as this. So uh, uh, another equation can be obtained by the fact that when coherent state acts on the eigenstate, when the coherent states are acted upon by an annihilation operator, they give an eigenvalue called denoted as alpha. So we know that we have described coherent states in terms of all states, we can write this as so we know that in order to be both relation to be valid, their right hand sides should be equal to each other. So we can make use of this by comparing both the right hand sides of the equation that have described above. So we have a kind of a recursion relation. So putting n is equal to 0, we get this, and putting n is equal to 1, we get this, C2. And making use of above equation, we can write it as this. So, uh, so we can continue this process for a while, and we can get the relation in terms of alpha n and square root n, square root n factorial and c naught. So we could see that the observation that we have obtained from the above recursion function. So putting back this into the definition we described as earlier as the coherent state as the superposition of the number state, we can put back this vector into the above uh, equation or definition that we described earlier. So now we have some kind of expression that is describing the coherent states as the superposition states of the photon number states. So there is still a C naught value. Uh, we can calculate it as with the help of a normalization condition, as the coherent states are the normalized eigenstates. So we can use it as this, and using the explicit form of the coherent states that we wrote earlier in terms of number states, and equating it equal to 1, we can get this form of C naught. So we putting back the C naught into the previous equation, we can get the final form of the coherent states in the form of in terms of number states. So this whole factor is a kind of a normalization factor that we were looking to calculate. So from this, we can calculate the probability of finding n photons in the field being in coherent states. So again, using the fact that we described earlier, in that form, we can calculate the probability of for n photons to be in coherent states. So we can see that an exact form of the Poisson distribution. So comparing the general form of the Poisson distribution uh, with the distribution that we obtained in the form of in the case of the coherent states, we can see that average photon number in case of coherent states are alpha mod square. So making use of this value of average photon number, we can calculate the correlation, second order correlation function, and it has the values equal to 1. So it coincides with the value that we described earlier or in the previous lecture in case of the Poisson distribution. So we can see that coherent states are the states that follows the Poisson that follow the Poisson distribution. And again, we could also calculate the fluctuation in the quadratures in the case of the coherent states, and we know that the fluctuation in case of Poisson distribution was equal to vacuum. So coherent states fluctuations does not depend upon the value of temperature, uh, as we can say that how much it doesn't matter how much the value of the amplitude or of the intensity of the fluid, the fluctuation is going to be always equal to the fluctuation of the vacuum fluid. So this is a very good quality and good property of some kind of state in from the point of view of experimental physicist. So coherent states are the good approximation of the laser field that we used in most of the experiments that we do in laboratories. So this is the uh, uh, these are the some properties of the coherent states. So we see that the coherent states have well-defined value, and if we plot these kind of properties and these kind of values in kind of a graph or a phase space, and we have space defined by the quadrature values. We can see that the coherent states are just defined by a circle with the diameter of 1 4, and they have a well-defined amplitude, and they are displaced from the origin by alpha. So, so many of the fields can be described by this kind of phase space, and uh, this visualization will help in order to discriminate between two, two or three fields or many fields, depending upon the properties that we have measured in the laboratories. So this is a very good way to visualize the field in terms of its quadratures. So this is for the coherent state. We saw that the coherent states are the annihilation or the eigenstate of the annihilation operator, and we can extract many kind of properties the from the Poissonian distribution of the coherent state, and we saw that coherent states are indeed the states that follows the Poisson distribution. And in the end, we saw that how can we extract some properties related to the second order correlation function uh, uh, of the case of the coherent states. So this is all for today, and in the next lecture we will see further properties and qualities of coherent states from the experimental and theoretical point of view. Thank you for listening and attending the whole lecture, and I will see you later in the next video. Bye bye.